moving a pair of polarizers to map out the angular anisotropy of the high harmonic generation. And then you couple a delay staging to here. And then you measure a spectrum for every one. So you end up having a four-dimensional data set. So it produces a lot of data, and we're trying to figure out how to best package that and deal with it in terms of the processing.
So I see you're using like organic crystals to generate terahertz.
Yeah, so we have.
Do you grow them yourself or you buy them?
No, these were bought. These were bought before my time in this lab. Actually, they're okay. So BNA, I mean, my understanding of BNA is that it's kind of, it can be hit or miss. So, you buy, let's say you buy 3 crystals, and then only one of them is probably very good, and then you find the damage threshold on the other 2. This was done by a grad student, or an earlier grad student, and they calibrated the field strength with just based on the electro-optic response of gallium phosphide. Currently, our time domain spectrometer is just running on ZnTe, so it's more of an analytical tool than a high field pump source. So we've looked into some of the Spintronic emitters as well. The company THz is making them now, and they're supposed to be coming with a high field source at some point, but it's it's a new company, so it's a bit slow. The first people to do this Spintronic emission, and their base emitters get up to like 200 kilovolts per centimeter or something like that. The new generation is supposed to get up to around 1 megavolt per centimeter. And the one thing that is nice about those is they're insensitive to the input polarization of the laser pulse. So the output polarization of the terahertz is determined by a permanent magnet, so the magnetic field that you place on it. And so one of the things that we're especially interested in those for is some of these magnon modes are sensitive to so you're basically driving the magnon with the magnetic field component of the terahertz pulse, but it's sensitive to the crystal axis that you are exciting on. So you can put your sample on a rotation stage to align it, or you can rotate the terahertz pulse itself to align it. And so, lithium niobate is great because it's a rock. It doesn't damage all that easily.
Right.
But the control of polarization is definitely a big challenge. So I think our plan is sort of to we want to be able to use lithium niobate as a high field pump, and then sort of explore these newer high field sources as they become available. I've had one on order now for like 4 months, and the first batch got screwed up, and so it's always a bit of a slow process.